I'm going to start recording so I can say welcome back to everybody who is here and welcome back to people who are watching later. We have 22 out of 28 of you who've done your course evaluations. So just as a reminder, if I can get that number up to 26, everybody get, we're so close. I need 4 more of you. So spread the word. So if you get 26 out of 28, my deal was everybody gets a point of extra credit. And if you do the separate Qualtrics survey, that's not a university thing, that's just something I do separate, then you get another point for doing that. So the university course evaluations close Saturday night. The Qualtrics survey is open through the end of finals week. So you have time to do both of those still. So yes, do some peer pressuring. Ask your friends if they filled out their evaluations. So we have more material that is left than what I reasonably have time for in one class. So whatever we don't cover today, there will be a separate video for it. So just as a FYI. Question?
Yes, what about differential item functioning? Because we didn't cover any example for that, but it is the same if we test the IFA invariance transforming the parameters.
Yeah, I don't have a diff example that does A's and B's directly because M+ doesn't do that.
Great.
So I didn't show the traditional IRT side, but if you understand the concepts, then you should be able to figure out software that will do that for you.
Okay.
There's probably 8,000 different R packages that will just do, diff types of things. Certainly within, you could probably do the constraints and stuff like in MERT and those sorts of things too. But yeah, I don't have an A and B invariance example.
Okay, thank you.
But I do have all of this. So as it notes on the bottom here, I don't do path analysis in this class. I do it in the generalized linear modeling class because path analysis is basically just a bunch of regressions using observed variables at the same time. Has nothing to do with measurement per se, so that's why I don't put it in here. So the lecture was originally titled Path Analysis in SEM, and when I realized I was going to not have time for that, I took all of that stuff in because it's literally a duplication of what I did either. So if you haven't seen path analysis before, I have a whole lecture and several examples from the generalized class that will go over that. And the generalized class is coming back in the spring. So if you want to see it live, you can do so like in April. I hope the generalized class should be offered every spring from now on, schedule permitting. So what we have then is SEM. This is organized by a couple of slides about sort of standard SEM and describing the distinction of exogenous versus endogenous, which is surprisingly not easy to understand. And then the rest of it is sort of talking about alternatives to SEM that people either do or recommend, and some considerations to think about if you can't do everything that you want to do in one simultaneous model. Then I also have an example. So example 9 here, which is the finale, a full structural equation model. It is the same data that I showed last week when I was talking about fighting with my dissertation committee about whether I needed a latent factor. I also did fit these models in R, so there's output and syntax that you can download for Lavon to do all of these things as well, although Lavon doesn't do latent variable interactions, so I couldn't do that part. So all of those resources are available online as usual. In terms of work that's outstanding, let's see, homework 6 in this class is due at the end of finals week. Does anybody want to ask me about that? Any questions on homework 6, which is invariance, doing CFA and IFA style? Not yet? You got 8 days, so it's plenty of time.
I have no questions because I have not started it.
That's fair.
Yeah.
Fair enough. Well, next week, we're not meeting as a class, but I am in office hours all of the time that I would normally be teaching. So 12:30 to 3:30 Tuesday, Thursday, as well as 3:30 to 4:30 Monday, Wednesday. If you want to just come and hang out, like without questions, but just to like force yourself to get it done and to get help immediately, that would be fine. Because sometimes I know how it's like if you get on a roll and then you get stuck, And then you have to email me, and then you have to like go find something else to do. Like sometimes it's easier just to like do it all at once. So if there's anybody who's wanting to take advantage of that extended time to work together, we can be Zoom buddies, and that'll be fine. Anybody who has not turned in homework 3 or homework 5, please let me know via email as soon as you do. That way I can try to turn it around to you as quickly as possible so that you may have a chance to revise. All right, so then shall we? The grand finale? SEM, the big picture. So the distinction of SEM is basically that term gets applied when you have latent variables where there's more than one, and you are testing hypotheses related to how they predict each other. So technically speaking, you could consider higher order factor models, multiple factor models as structural equation models rather than as confirmatory factor analysis. It gets to be a bit of a semantic distinction. But SEM is the term that is used when you're interested in regression type relationships. So does X predict Y? Does X predict Y after controlling for Z? Like those kinds of questions. But you're willing to build measurement models to represent those variables rather than using observed variables. But other than that, everything you've learned about how to do regression type models directly follows. So there's not much that's different if you're working with latent variables rather than observed variables, other than that things are harder to estimate. The difficulty in doing SEM comes in building the measurement model, figuring out why it doesn't fit like you thought it would, and what to do instead. So it's not a coincidence that like I spent all of the semester on the measurement side, because that's the tricky part. Once you get all of your measurement models built, putting them into the same analysis and adding 1 or 2 directed arrows between them is much easier. So that's the part that we're at. So just to remind you then, measurement models, we would use the phrase confirmatory factor analysis if we're pretending our indicators are continuous and normal enough. IFA or IRT or CFA for categorical outcomes, all of those words basically refer to the same type of model, where we've swapped out our linear relationships for something that's nonlinear. We've swapped out the distributions. It would still be called IRT if you have nominal variables, and it could be called anything if you have some other kind of link function. So like a generalized SEM would be like a measurement model for counts or zero inflated variables or anything like that. In all of these cases, though, the factors themselves are assumed to have a multivariate normal distribution. So the distinction of CFA versus IFA versus whatever is irrelevant when we're talking about the structural model. They are all continuous variables. So we have path analysis essentially using those multivariate latent variables as the basis of SEM. You can add in other observed variables. So other boxes could be outcomes or predictors, however you're thinking about those things. Not every box needs a measurement model. So for instance, if I wanted to control for age in an analysis, do I need a measurement model for age? No, I need a calendar. That's what I need. I don't need to ask you like, indicator 1, how old were you last year? Indicator 2, how old were you the year before that? Like, no, it's not latent. So boxes are fine if you have something that can be measured directly. So you can put in whatever kind of observed variables you want, and depending on your software package, they can have different distributions. So M+ has a lot of flexibility, Stata has a lot of flexibility, R Levon, not so much. The one catch is that if you're dealing with categorical predictors, in M+, there is no easy way to say it's a factor variable and let it do the coding. You have to make all of the dummy codes or the contrast codes yourself as separate boxes ahead of time. So that can be a bit tedious, but that is the way that it works. So there are all these rules about how to make sure that your structural equation model is identified. And to be honest, I didn't learn any of them well enough to tell them to you because I don't think they're needed. Your task in trying to figure out if your model is identified really should be focused on the measurement part. So each factor needs a scale. It needs a mean and it needs a variance. We got 2 options for giving it a mean. Do you remember what they are? Say it's 0, or If you wanted to estimate a factor mean, what would you do instead to make sure that that's identified?
Set one marker item, intercept
Yeah.
0.
Fixed an intercept or a threshold to 0. On the variance side, to make sure that all latent variables have variances, you can either fix it to some number like 1, or do what? Fix what instead? Marker item
Factor loading.
loading. Yep. Yep, so either the loading or the factor variance, not both. If your latent variable is going to be predicted by other stuff, then you want to use a marker loading. So its variance can become variance left over. Yep. If you have, let's see, how many indicators do you need for your factor to be identified?
3.
3. If you only have 2, what do you have to do? Equal loadings, at least at first. It is technically possible once your factor relates to other stuff for the loadings to be unequal, but that's usually where your model's going to break. Then otherwise, basically, in terms of the structural model, my advice to make sure that it's estimable is don't do anything stupid. Like, don't put in things that are logically impossible and you'll be fine. So examples of logically impossible would be something like 2 variables have both a correlation between them and a regression slope. That's not logically possible to differentiate those because there's only one covariance. So as long as you don't put things in that are redundant, you should be okay in terms of identification. So in terms of adding stuff then, terminology that gets introduced in SEM in particular is describing variables that are observed as either exogenous or endogenous. And this is confusing because it's not as straightforward as one might think. So I have a mnemonic to remember what these words mean. Where exogenous, I emphasize the X, meaning that we're talking about these as being predictors. Like X's in my notation is always a predictor and Y is an outcome. The alternative is endogenous, which I remember as endogenous, meaning that the arrows are going into it, it's an outcome. So here's an example path model. In this case, we would say that we have 2 exogenous variables, x1 and x2. These are predictors because they have arrows going from this box to another box. The variables that have arrows going into it are outcomes, are endogenous. So in a factor model, all of the indicators are endogenous outcome variables. This entire semester, I've avoided this terminology because outcome and predictor is enough. So the only part that really we haven't talked about is this 2-letter word right here. Do you see what this word says? On. That's it. On means a regression. The way that it works in M+ is it's Y on X, meaning X predicts Y. To avoid getting this backwards conceptually, think about the on as an equal sign. If you were to write out an equation, you would write Y equals predictor, predictor, predictor. It goes in the same order in the code. Y on predictor, predictor, predictor. So to estimate the relationships among these 4 boxes here, these 2 statements would get them all. I have x1 and x2 predicting both y1 and y2, and I have a covariance estimated between y1 and y2. So conceptually, I have 2 outcomes. I'm allowing them to be related. Each of these outcomes is being predicted by x1 and x2. And this is what the equation would look like if I use superscripts to try to keep track of what fixed effect it's predicting, what outcome the fixed effect is predicting. In SEM and path model diagrams, you will either see the idea of residual variance with a separate latent variable that is going into the box. So this is the convention that we used in measurement models, is having like an E circle that goes into the box. Otherwise, you will see what should be a curved arrow where it's going into itself. PowerPoint doesn't do curved arrows very well, so mine is blocky, but that's what this means. If you see a box or a circle with 2 arrows going into itself, that it's the idea that it has an estimated variance. Okay, with me so far? So this is what I would call a multivariate regression. I'm predicting two outcomes at the same time, and I'm allowing them to be correlated because they come from the same person. Seems reasonable enough. Here's an alternative model where, in this case, we still have two endogenous variables, but this is an example of a model that you could not do in standard regression software. So the path model on the top part here, I could do in any kind of regression type program by tricking it into being a multivariate model. The bottom, I could not, because Y1 is now a predictor of Y2. So Y1 is both an outcome and a predictor at the same time. And this is really what path analysis was designed for, is this situation when a single variable has to play different roles. In this case, Y1 would still be endogenous because it is still being predicted by X1 and X2. And then do you see the difference in the code between these two models here? I switched the with to an on. So with is a two-headed arrow, meaning they just covary, and on is a single-headed arrow that's pointing to the term on the left. So think of on as an equal sign. So this should be straightforward, but it's not. You have choices either that you get to make or that are made for you, depending on what software you use, as to what happens with these exogenous variables, predictor variables. So what parameters get estimated is going to vary by program based on how it's treating predictors. So if you leave your predictor as exogenous, just like treat it like a normal predictor, like in a regression model, you cannot have missing data on it. You can't, because each case needs to be complete in order to get a predicted outcome for each person and to get the residual variance. So any cases that are missing predictors get deleted. But the good news is that then the predictors also don't have distributional assumptions. That's a common misconception when people are initially learning regression, that like all the variables in the analysis have to be normally distributed. No, they do not. Predictors can be anything they want. Otherwise, we couldn't have something like ANOVA, which is using predictors that are nominal or categorical. So this is not great, as you might imagine. And it's also not well understood. Wait, but if I'm using full information maximum likelihood, doesn't that handle missing data? No, it handles missing outcomes, not missing predictors. So you can trick the programs into thinking that a predictor is actually an outcome, even if it is not being predicted. So you can force an exogenous variable into the model likelihood by asking for the program to estimate its mean, its variance, or its covariance with something else. Then, even though the variable is not being predicted, the software thinks it's an outcome. Its summary statistics, its mean variances and covariances are then things to get found during the likelihood search estimation process. So that's both good and bad. The good news is that then you can have missing data. It's assumed missing at random, the same as for any missing outcome. The bad news is that you then have a distributional assumption that you're making. So if I had, say, for instance, a binary predictor that was missing for some of my cases, I could bring it into the likelihood, but then I'd have to say that it's continuously normally distributed. Not ideal. In M+, at least, in theory, you should be able to say, no, it's binary, let it be categorical. But that only works if it is literally an outcome being predicted by something else. So if I wanted to do that, I'd have to make up another variable to predict my binary variable so that it's an outcome officially, and then it could be binary and still have missing data. So this exogenous versus endogenous is not clear-cut with respect to whether something is a predictor or an outcome. I have a little bit of information about what happens in other packages. So in some packages, such as in SAS's SEM package KLIS and in Stata's, it forces, if you ask for full information maximum likelihood, it forces all the variables into the likelihood for you. You don't get a choice. So then your predictors are being treated as outcomes with distributional assumptions. So there's a little bit about that, but I don't want to dwell on that too much. So here's what I'm going to say. Is your variable in the likelihood? If it is, then I'm calling it an outcome, even if it's not being predicted. If it's not, then we'll call it a predictor, and it would be truly exogenous. So this is part of the reason that if you read older SEM textbooks, they say things like, all variables have to be normally distributed, because that was true in the software at the time the book was written. So full information maximum likelihood does allow you to keep cases that are incomplete, but only if you're willing to take your predictors and pretend they're outcomes. Then they have distributional assumptions, but then they don't get kicked out of the model if you have incomplete cases. In Levon, in the version that is currently available, you get a choice. You can leave it exogenous as a true predictor, or you can bring it into the likelihood. The same is true in M+. Why this matters is in thinking about degrees of freedom and model fit and what counts and what doesn't count. So if I have covariances among variables in the likelihood, they count with respect to counting towards your degrees of freedom and estimated parameters, and they count with respect to misfit. So if I have two outcomes that are correlated, and my model says they're uncorrelated, then that's going to hurt my fit. It's the exact same thing that we've seen all semester. The factor models predict a pattern of correlation. If they get it wrong, then your model fits bad. If they get it right, your model fits well. Covariances between variables that are considered exogenous predictors that are not in the likelihood with endogenous outcomes that are in the likelihood also count towards your misfit. So if I have a model that says x1 predicts y1, but x1 does not predict y2, and x1 and y2 really are related, then that's going to hurt your fit. But the last one, covariances among the predictors that are truly exogenous do not count. They're not estimated, and they don't count against you if you leave them out. That is true in regular regression as well. Like if you fit a regression model of any kind, you don't get covariances among your predictors as part of that story. The slopes of the predictors take into account the covariances among the predictors, but the covariances themselves are not estimated parameters. They don't need to be. So this is helpful in thinking about like what are the possible reasons why something could not fit. Any relationships among the predictors are not part of the reasons why you don't have good fit. It's only relationships that involve variables in the likelihood, outcomes. All right. So my approach to building SEMs is to focus on each measurement model first, make sure that that fits adequately. As long as you have at least 4 variables, you can do it separately for each. Then to combine all of the latent factors that would be part of your analysis to answer your research questions into a simultaneous model. It is helpful, I think, to start with a model in which all of the latent variables are just correlated. Like don't put paths in, just let undirected arrows everywhere, just to see what's related to what. So we did that with the higher order factor example, for instance. Like what is the correlation pattern among these 5 things? Knowing that then tells you what the bivariate associations are among your latent variables, which is a logical precursor to examining unique associations. So if variable x and variables will go y1 and y2 aren't related to begin with, then it shouldn't be a surprise that they're not related anymore after controlling for other stuff. So the same logic by which you would look at bivariate correlations in a Pearson correlation matrix before doing a regression model, the same logic applies here. We would want to look at bivariate latent variable correlations before putting in directed arrows that focus on the unique effects of each predictors after controlling for other stuff. Fortunately, though, you can get that information without actually having to estimate the correlations directly in a separate model, and I'll show you how to do that. All right. Do you want to see an example? Good. Any questions so far? Yes.
Those covariances that we can estimate between the predictors and the outcomes when the predictor is not in the likelihood, that's the correlation, so the regression part, right?
Yeah, so if you want a relationship between a predictor that is not in the likelihood and an outcome that is in the likelihood, you cannot estimate a covariance directly because that will bring the predictor into the likelihood.
Oh, so
It has to be a directed path from the predictor to the outcome in that case.
a regression coefficient.
Yes.
But when the predictor is in the joint likelihood function together with the outcome, in those cases, that relationship will also be a regression coefficient or a covariance
Yes.
index?
So let me, 1 second here. Let me go back to the picture. So in this picture, x1 and x2 are exogenous. They're predictors, and they could be in the likelihood if I want them to be because of missing data, or I could keep them out. But if I changed this directed arrow right here, I'm trying to click on it, that arrow right there, if I change that to a two-headed arrow, with a covariance, then that would force the x1 predictor into the likelihood. By the way, the rest of the time when we talk about these arrows, they're slopes. These are fixed slopes. But in this context, they become direct effects. It's a slope, though. It's not new. It's just a switch in how we talk about it, and I do it unconsciously, but I need to remind you that, no, this is not new. You know what an intercept is. It's the predicted outcome when all of your predictors are 0. We've talked about intercepts and thresholds all semester. These directed paths are just slopes. They're not different than any other slope in the rest of your life. A slope is the change in y for a 1-unit change in x. The directed path, the directed part is because you can also have what are known as indirect effects. So in this bottom picture right here, the indirect effect between x1 and y2 would be this slope right here multiplied by that one. And the multiplication of those two slopes is known as what is an indirect effect. So a direct effect is between just two variables, an indirect effect is between at least 3. Because you can have like a chain of indirect effects going, path.
And is it multiplication because of like probability rules of like this and this? Or
it's multiplication because of the rules of how the predicted correlations are recreated by these models.
great, thank you.
Yeah, so it's in the same way that like in the factor model, right? We have our factor, and then and it's this loading times that loading. Yep. It's that path times that path.
Great, thank you.
Yep. And so in this case, like what we're saying is that x1 is related to y2 directly, so we got that path there, but it's also related indirectly through y1. And so then mediation would be the extent to which this direct slope right here, the path from x1 to y2, changes after you control for y1. That's mediation. I will have some examples of how you can estimate indirect effects because it's a common thing that people like to do. But to me, mediation and indirect effects is nothing more than regression with a better marketing campaign to support it. Because it's not different. Like, there are so many hypotheses that are phrased as, do these things still relate to each other after controlling for blah? That's the exact same thing as an indirect effect. It's not different. So I won't drink the Kool-Aid. I just won't. Yes?
In terms of degrees of freedom, to estimate the covariance of the regression parameter is exchangeable, right?
Yes, yes. So if you put in a two-headed arrow or a one-headed arrow, you spent 1 degree of freedom.
Okay.
Yeah. So these models are actually just identified if x1 and x2 are exogenous, because this relationship between the two of them doesn't count. But if I brought x1 and x2 into the likelihood so that I could have missing data, then the fact that I don't have a relationship between them would count against me. It's confusing.
Okay.
Yeah. All right. Example, though. Unless there's other questions before we dive in. All right, so all of the files that go with this example are online. I'll just hit the high points here. So as I said before, this is the study from a week or two ago, my dissertation. I was able to publish these 2 papers out of this study. And you can download those to see how I would talk about the results from this analysis. Probably would do a better job now than what I knew how to do in 2006. But, you know, science is self-correcting, as they say. So here's the M+ code then that would cover all of the reading the data and what variables we're using, estimation options and stuff like that. So this data set has a bunch of variables in it. I am asking, we're treating these all as continuous. So this is like a CFA basis kind of SEM. The code, you know how to switch it if you need to do IFA instead. So we're using robust maximum likelihood as our estimator. You've seen most of this before, but there's a few new ones. SAMPStat stands for sample statistics. That can give you extra descriptive statistics for your data. That's useful just to check to make sure it read your data correctly, because you should be able to like match the means and the variances. They are going to be estimated using maximum likelihood though, so they won't exactly match what you would get out of descriptives, because that's REML instead of EML. You're familiar with the cheat codes. Those are still here. Standardized solution, residual solution. There's 2 new ones here. S values asks for a piece of output in which your model code and the parameters that you ended up with are all written in one syntax piece. That's useful if you want to provide start values to make your models estimate faster. It's also useful if you are going to build what are known as plausible values, which is a section of the handout that is forthcoming. So that's a new one. And Tech 4 is latent variable correlation matrices. So that one is, I think that was in the higher order factor model example, but otherwise we haven't seen that because it hasn't been relevant. And I'm also saving factor scores for each of the measurement models that I'm going to show you, because one of the last analyses is I want to show you how the results would change if we did latent factors directly versus if we treated the factor scores as observed variables. So as a point of comparison, basically. All right, so first model, we're running through just the measurement models because that's what I would do in practice before going to the giant SEM. So the first construct that we are, I'm running out of words. The first construct that we're examining, can you tell it's the last week of classes? I think I've spent all my words. I'm just, I don't know. You know, factor, code, see? Questions? No. We are building measurement models using confirmatory factor analysis. So I've got 6 indicators of what is supposed to be visual impairment in these older adults. In preparation for my factors to eventually be put together, I've switched my method of identification into using a marker loading and estimating the factor variance. I also have code here that gets omega, the reliability of a sum score under this measurement model, and you've seen all of that before. In the Levon code for this, I found an omega function in the SEM tools package. And so in the example code online, I used that to get omega, and it did match to the 3rd decimal place. So yay for that. So here's my measurement model results. What do you think about my model fit here? Good or not good?
Quite good.
Quite good. Yeah. My chi-square is actually non-significant. I know, like that never happens. I have like 150 people, by the way, so that's part of the reason. And you can kind of tell that by looking at the size of my confidence interval of my RMSEA. It is quite wide. Somewhere between perfect and terrible is what my RMSEA actually is. With an average of 0.07, so sort of in the normal range. CFI, TLI, what are these supposed to be? Big or little?
Bigger.
Big. Yeah, these are relative to the null model. How much better is my model than the worst model? This is the one that you can ignore always. The fit of the baseline model. This is null versus saturated. This has nothing to do with your model. And SRMR is also happy. So here's my solution. This is the unstandardized solution, and all of these variables are on slightly different scales, so we can't really tell how good the loadings are just by looking at that. I do have the standardized model down here, so here's my loadings. These are, they're kind of like, they're at least positive and sizable, but they're not great. So the omega for this model is only 0.816. So traditionally acceptable reliability, but not super great. The other thing that I computed here is factor score reliability. So omega is reliability of a sum score. So if I was just going to add up these items and make them a box, then I would expect 81.6% of that box to be reliable and the rest to be error. If I were going to output factor scores from this model, then the reliability of those factor scores is the variance of the factor divided by that plus the standard error squared. So the idea of true over total. And the factor score reliability here is a little bit better. So I think that if you're going to report reliability, it should match your intended use of the variables. If you're going to use factor scores, I would report that reliability. If you're going to use a sum score, I'd say, what are you doing? But, you know, people still do that. You can use omega for those. Okay. Here's the normalized residuals to check on misfit. So nothing really super big here. The biggest one is between two of my indicators that shouldn't have any extra relationship, so we'll call it good. Next thing in the story is a latent variable of driving impairment, which is indicated by observed outcomes during a driving simulator course. So I have 6 indicators of driving impairment. I have my marker loading here for the first one. I've got my omega. This is a standard CFA measurement model with the exception of one thing right here. I have a residual covariance between two of my indicators, which is the amount of time it took to complete the course and the number of speeding tickets you got inside the course. As you might imagine, those are negatively related to each other. People who speed take less time to do it, which is why we speed, quite frankly, right? No one speeds just for the fun of it. It's to make wherever you're going faster. What do we think about this fit?
Acceptable?
Yeah, it is not worse than perfect, but this one, CFI TLI, is not really as happy. I think this is a function of the fact that the correlations among these indicators are not that strong. So it's harder to say how much better it is than the worst model of no correlation if you don't have a lot of signal in your data. So it can be the case that RMSEA is super happy with you and CFI hates you. Like, these things aren't going to agree because they're based on different reference points, and they each have their own sort of idiosyncrasies with respect to when they would be more or less valid. So there's a book chapter on your reading list that covers sort of the most recent research and the behavior of these things. Sometimes it doesn't work as well as other times. All right, here's my model results. Standardized model. So yeah, what do you think about this as an effect size, standardized loadings here? Not that high. So time to complete the course in particular doesn't even load significantly. So this latent variable is not going to have a lot of reliability. I can tell you that right now. An omega of 0.5. Yeah. Something to keep in mind, if I don't get the results I want, this could be part of the problem, is that I don't have a good measurement of this. These indicators, I got 6 of them, but they're not that related to each other. Factor score reliability, only 0.7. So better, but still not great. Okay, next measurement model, attentional impairment, which this is the one that lumps together the 3 different tests so that we can talk about them as one construct. So this is a 3-indicator measurement model. How well is this going to fit? if I only have 3 indicators of one factor?
Identify.
It's just identified, right? So how well is it going to fit? Perfectly. It doesn't have a choice. I have spent all the degrees of freedom. Essentially what I've done is trade 3 covariances for 3 factor loadings. So why am I doing it? To get the omega. That's why. So that I can report that along with everything else. And the omega for my 3 indicator factor is 0.75. Not surprising given that there's only 3. So, factor score reliability, a little bit higher, 0.8-ish. Okay, cool. Now we're ready to do the SEM. Here's my picture. I've also lost my consonants in addition to my words. This is my picture. This picture was drawn by M+'s algorithm. For the longest time, M+ never had a diagrammer, and the mutanes swore that they would never put a diagrammer in it because they thought the diagrammer was like the work of the devil, and it caused people who didn't know what they were doing to draw pictures and estimate crazy models. It made it too easy, right? That's a common thing with statistics. It's like you need to make the package difficult to use to keep people from just doing it stupid. That's what it is. Like it's like a rite of passage. So where did this diagram come from then? Their head programmer, this is a story that was told at a conference. I wasn't there, but I heard it like secondhand. Their head programmer's son, who was 13, made the diagrammer as a class project. So we can all feel really good about ourselves in this moment that the 13-year-old wrote a program, just for fun, on the side to make these diagrams. And Bent was so impressed that he's like, I got to put it in. So he went back on his perspective, and the 13-year-old's package is drawing diagrams. So there is an option, like when you run the model to say, do it with a diagram, and there's a file that gets created that you can then manipulate. So it didn't look quite this pretty when it came out, but you can drag these things sort of around to split them. I tend not to do diagrams in the packages. I tend to make them myself in PowerPoint so that I don't have to fight with it. But one nice feature is that it puts all the parameter estimates on there. So that can save you a lot of time. And you can choose whether they're standardized or unstandardized. Amos is another package that does SEMs that has a nice diagrammer. That's an SPSS add-on. Do we have that in the virtual desktop? Does anybody know? I thought maybe we did. I learned Amos like 20 years ago or something. I haven't used it in a very long time. So this is the model that I wanted to estimate, okay? Let me see if I can get it all on the page here. So I have age. Generally speaking, in your diagrams, you want to go either top to bottom or left to right in terms of the direction of your relationships. So I've got age here sort of on the top left-ish. Age is going to predict vision. So I expect that people who are older are going to have more visual impairment. I think that age is going to predict attentional impairment as well. And here's my driving factor. I think that all of these things are eventually going to predict driving impairment. But the question would be then, like, does age predict driving after controlling for attention and vision, for instance? So we can talk about unique effects of these paths and indirect effects as well. There's one other thing over here that P speed, this is processing speed, this is what's known as a single indicator latent factor. It is a trick. It is not anything other than just treating this as a box. What I did, you can tell in the code here, make a new latent variable out of that single indicator, and I fixed that indicator's loading to 1. I fixed the indicator's residual variance to 0. So all I have done is taken the information from that box and moved it over to a circle. Ask me the logical question.
Yeah, why?
Why? That's the question. It doesn't change the math any. But what it does do is then in the Tech4 output of the correlations, it brings this into that, whereas it would otherwise exclude it. and I want to think about processing speed as another latent factor, like conceptually, and to look at all of the others. So it's literally just a trick to make the output more manageable. Now, what people will sometimes do with this is, rather than saying, I have a new latent variable that is perfectly predicted by, or perfectly captures this old one, they will do a reliability correction. And I will show you the code to do this, but the idea would be, let's say that I have an observed variable that I have a reliability coefficient of 0.8. I can set it up so that 80% of its variance goes to the factor and the other 20% goes to the residual. That would be a more reasonable thing to do in instances in which there's some reason why you can't do a simultaneous model, but you still want the idea of correcting for unreliability in your measurement. So I've got that in the code here later on, but that will probably be on the video and not that. Okay, so the structural model then is just identified. How do I know that? Every possible pair of my variables, so I'm counting age and I'm counting processing speed here, there is some kind of relationship directly between all of them. Attention and speed are correlated. Otherwise, everything is predicting a single-headed arrow from the circle to this circle. So what does that mean with respect to my structural model fit if it's just identified? It's as good as it's going to get. So this would be a baseline against which I would judge any changes to the structural model, such as deleting non-significant paths or otherwise trying to make it simpler. This is as good as it gets. So it's directly analogous to the idea of the saturated structural model from the higher order, where we just let all the factors have a correlation. This is mathematically equivalent to just letting all the factors have a correlation because every pair has some kind of path between them. So I will get the direct slopes in the output, but then I will also get the model implied bivariate correlations out of Tech 4. So I can get both versions simultaneously. Okay, with me so far? So then the code, I wrote out everything that's in this model. But all you would really need is the loading parts, the residual covariance, the intercepts, all the residual variances, the factor variances are estimated by default, and the factor means are fixed to 0. So all of those things would happen without you having to type it. Here's the new piece, just this much. So I'm on page 8. So these 4 variables are latent variables defined by the measurement models already. So there's my vision, there's my driving, there's my attention, there's my speed. All 4 of these are now considered latent variable outcomes of age. And these are labels. So age 1 is the regression of age predicting vision. Age 2 is age predicting attention. Age 3 is predicting speed, and age 4 is predicting driving. Likewise, I have attention, speed, and driving being predicted by vision, and I've got 3 labels for those fixed slopes. Attention and speed, I wanted to have a covariance instead. And then last but not least, I have driving also being predicted by speed and attention. So the logic is age makes you see worse, seeing worse makes you a worse driver. Fair, right? Age should make your attention less strong. Less attention means you're a worse driver. The question would be then, after controlling for vision and attention, are old people worse drivers? The answer is no, by the way, according to these data. Here is an example of how you can get indirect effects. to examine such kinds of mediation style questions. As with any other computed quantity out of your output, it requires labeling the ingredients and then asking it to do the math. So I'm using model constraint. I am creating 3 new computed quantities. Age vision is the indirect effect from age to vision to driving. That is age 1 times vision 3, which means the path from age to vision multiplied by the path from vision to driving. So if I go back up to the picture, it's that slope times that one is what I'm asking it to do. So age 1 refers to whatever this coefficient is going to be in the estimated model. Vision 3 refers to whatever this slope coefficient is going to be. And I've got 2 more just to show you what that would look like. Age to speed to driving, and then age to attention to driving. So the only new thing is on as a new type of relationship. That's the only thing that you guys haven't seen yet. Okay, how are we doing? Overwhelmed, or are you just like whelmed? I know you're not underwhelmed, because that's not possible, right? So let's see what happened. Overall, model doesn't fit. My chi-square test is now significant. So it's significantly worse than perfect. However, because of my preliminary measurement model checking, I can narrow down the reasons for misfit. I got 110 model degrees of freedom that I could spend in here. The reason for misfit has to be mispredicted relationships between indicators from different factors. It has to be. Do you know why? Because I already verified that each set of indicators measures its factor, and the factors did a good job of predicting those correlations. Also, every possible relationship among my factors is in here, either as a covariance or a directed, so that can't be why. So the reason that the model is significantly worse than perfect has to be because like something over here wants to be extra related to something over there. It's across factor relationships. But if I look at the rest of this, RMSEA is perfectly happy with me. SRMR is fairly happy. And these are, let's go with adequate. So then in the output, you get your list of measurement models. So the by statement, these are all my factor loadings. Then we get the on statements. So this is attention on vision. The way that you would think of that is vision predicting attention. Y on X. So that has a regression slope of 0.287. So this is the change in attention for a 1-unit change in vision. A slope is still a slope, and it's significantly positive. So that means that people who have more impairment in their vision have more impairment in their attention. Other significant ones, attention significantly predicted driving. There's a positive coefficient, so for a 1-unit change in attention, driving is higher by 0.3. So all of these are scored to measure impairment. So people who did worse on the attention measure did worse on the driving task. People who are older see less well. People who are older did less well on the attention task. But age is not a predictor of driving after controlling for attention, speed, and vision. So the direct effect of age on driving is not significant. Covariances then are given last. That's my with statements. So whatever is left over in attention and speed after being predicted by age and vision is related positively. And this one is within the measurement model for driving, speeding tickets, and time to complete the course. Last but not least, indirect effects. There's only one that would be significant by conventional standards. It is the relationship between age, attention, and driving. So what this means is that part of the reason why, basically, let me say it this way. The relationship between age and driving is different after we control for attention than if we don't. That's what that means. So part of the relationship between age and driving is because age predicts attention and attention predicts driving. That's why. So your standard indirect effects. M+ has built-in things to get indirect effects for you, but it only applies in some types of models. This let it multiply it yourself strategy works all the time. This p-value will probably make reviewer 3 mad if you try to report it. You'll have to do some sort of like bootstrapping or some other kind of like fancy thing to make it more palatable. There's a whole line of research about that. Basically, a wall test isn't going to work for 2 terms that are multiplied together because that distribution is not going to be normal. It's going to be some kind of skewed. So there's like 8 million people who've worked on this problem and figured out that bootstrapping of various kinds can help make it more accurate. And it's 3 o'clock, and apparently we're all supposed to be done because all the lights just went out there. It's only Thursday. All right. So the on statements are just the extra layer here that you haven't seen before. These are how the latent variables relate to each other. Oh, they heard me. Okay. It's back on. In the standardized solution, then, these are all given in a correlation metric instead. So if you learned standardized coefficients like in regression class, that's what these ons are in the standardized solution. Those would be more commonly reported in path model diagrams because people know like how much a standardized slope of 0.2 should be. Here is the output from Tech 4 that summarizes the bivariate relationships among my 4 latent variables: vision, attention, speed, and driving. So this will tell me to what extent these things are related. The model that I set up with all the directed slopes will tell me which things are still related after controlling for the other predictors. So it's 2 different pieces of information there. So given some of my directed slopes being non-significant, such as age predicting speed and age predicting driving, I did a revised model where I kicked those terms out. So if I kick out terms, can I make my model better or worse? If I simplify?
Worse.
Worse. So if I want to justify my decision to kick something out, then do I want a significant model comparison or non-significant? Non-significant, exactly. So I did the -2 log likelihood difference test between my previous model and this one with 2 paths kicked out. It's non-significant, so yes. Evidence suggests that my model adequately recreates the pattern of relationship among the latent variables. And I don't need those 2 paths. Okay. 302. How are we doing? We're in there, right?
Yeah.
Now, what if you wanted to do moderation? I know. Nikki's like, no, I don't want to.
Well, you mentioned mediating earlier,
Yeah.
and I was like, I still struggle with what's moderation and what's mediation.
Moderation is interaction terms. Mediation is the idea that this causes this, which then causes that, and that's why these 2 things were related.
I will probably still always ask you the difference between the 2,
That's
but
fair.
I don't want to do interaction terms.
You don't want to do interaction terms. Fair. Well, here's the thing. Normally, how do we do interaction terms? We just multiply 2 predictors together, right? What if I want to know whether the relationship between attention and driving depends on vision? Could I ask that question? But how do I multiply 2 circles? Ugh. Turns out that's very tricky And that's another thing that people have worked a lot to figure out how to do. And M+ does it directly in a way that makes sense and works well, and Lavon doesn't appear to have that option. So I looked for it, I couldn't find it, and I gave up. But it turns out to be actually really straightforward to put in the code. So what I'm adding then, oh, I just missed it. I was going to show you the circle. I'm adding this blue circle right here. It's the interaction between vision and attention in predicting driving, where vision and attention are both latent variables. That's what I'm adding. The way to do it is X width. So what I'm doing in this code is asking for these two variables that are latent to be multiplied together, and the new multiplied product result I'm naming vis attention. So it's very much analogous to what you would do with observed variables, but it's in latent space. Visual attention, vis attention, the interaction term, is then being added as a predictor of driving. So conceptually, I have a main effective attention, a main effective vision, and I have their interaction predicting driving. Is that a question or?
So now we have like three. If we go back to the path diagram, we're essentially adding a new little circle, I guess, because they're both latent.
Yep, we are adding this blue circle. Yep. It is.
But it's not necessarily connected to.
It's not connected to.
Like vision and attention, I'm thinking of like the main effects that you were talking about.
No, so this is the idea of does the slope of attention vary by vision? Does the slope of vision vary by attention? This is the interaction term that allows us to ask that question. Yep. It does require changing your estimator. It requires numeric integration to do this, which is the same thing that IFA and IRT models use in full information maximum likelihood, where they do the rectangling. Yeah, the quadrature stuff, yep. And so that means that you can't have a lot of interactions in one model. You might be able to do one or two before it starts to break down. And because it's me, here's how you would do simple slopes to describe the pattern of the interaction. You know I can't let that go. It's my thing. So there's that part of it right there. So these values in here, these are the factor variances of the predictors. So essentially what I'm doing is doing -1 standard deviation and +1 standard deviation, and then asking what the simple slopes would be for high values of vision and low values of vision, and then doing the same thing for attention. So I'm asking for what is the moderator, what is the slope for a high person, a medium person, and a low person in terms of the moderation?
So that first square root of 0.443 is the factor variance for attention.
Yes.
Right? Excellent. And then the 224 is factor variance for vision?
Yes.
Right? That's what
Yeah, it's the other one. So yeah, so this is going to give me the slope of vision for somebody who is low in attention. Medium is the 0, which is going to be in the model already.
Yep.
And then this is +1 standard deviation. So the same logic in terms of how you would decompose an interaction applies even though they're circles. You just have to know what a unit is. And the unit depends on its variance. Fortunately, though, nothing significant, so we don't have to keep it. Yeah, but this is how you would do a latent variable interaction. All right, 307, that's enough of that. I know, it's like, I have my blankie on and I want to go home.
It's cold in here.
It is. It's cold in here unless you're standing here gesturing, in which case I'm actually sweaty, so, you know. I understand, though. That's me at home, like sitting in my basement. I have all the things wrapped around me. All right, so what I didn't get to, and no, I'm not going to keep going because I'm not that crazy, is what to do if you can't do a simultaneous analysis like this. So let me go back to my picture. Like, what if each of these latent variables had like 60 indicators? Like how, and I have 150 people. Like, I can't make all of that work at the same time. So then the question is, like, how do I take the analysis and break it into parts that I can do? And one strategy would be to just add shit up, basically take each of these measurement models, add the indicators, and make it a box. Another strategy would be to output factor scores from the measurement models and treat those as boxes, which is better. And then there's a third thing that is called parceling. Have you heard this term? Parceling is cheating. Parceling is adding up some of the boxes, but not all of them. So then you have fewer indicators. But in doing so, you're hiding all of the potential misfit of the ones that you combine together. So parceling is like an intermediate between adding shit up completely, it's adding shit up parceling, and it is cheating, so don't do that. So the rest of this then is a discussion of pros and cons of those ways of trying to shortcut the SEM by using observed variables instead, as well as the differences in the results for this analysis if we did it with observed variables versus factor scores versus latent variables. But that will all be on another video, which you can watch if you want to put off something else, or you can save it for your future self to enjoy. All right, questions? No, we're all overwhelmed. That's what I'm reading. But it's just as well, because it's 3:09. Well, if you think of questions in the future, please let me know. And with the few minutes we have left, then I want to say a very sincere thank you to every single one of you for sticking with us this semester. You all worked really hard. You showed up, you did your stuff, and I'm very proud of what you've been able to do. I hope that I will see you again in a future class. Either way, you have earned the right to bother me by being here. So that means in the future, if you're working on an SEM and you need some help, you can email me. That's allowed. And I can try to help you as best of my ability. The only thing that I ask in return is that 10 years from now, when someone emails you because they need help with their SEM, that you help them too. If we all keep paying it forward, then the world keeps spinning and everybody can keep growing. So thank you. Next week is just office hours on Zoom. If anybody needs extra help, email is fine too. Otherwise, I hope everything wraps up and I will see you on the other side in January. That is all for now. Signing off for the last time.
Thank you, Lisa.